The second example here is going to be a one-sided test, but that's okay because it's going to follow some of our previous logic. So in general, we've got a success rate of passing the rule of rose exam of 33%, and a policy is put in place to increase that by basically increasing the pain and suffering. So the question is really asking you, after the policy is put in place, do we have a greater than the prior pass rate situation? So, like before, that greater than aspect is going to help us define what our alternate hypothesis is. And so we're going to jump right down here and take those words which are going to define our alternate hypothesis, that our proportion is in fact greater than the historical test rate passage of 0.33, 1/3 of the cadets. Now, from that, that's going to define, by default, our null hypothesis to be less than or equal to 0.33. In this case, our test data is giving us that we've got 74 out of the 83 cadets that take this test on the second time go ahead and pass it, so we're roughly a 90% pass rate for the second takers. Okay, so now looking at our test statistics, we can go ahead and do some of our test cases where our n times our proportion is equal to 83 retakers times our population proportion of 0.33, which gives us 27.4, which is greater than 5. So that's marching in the right direction. And then if we do our NQ, n times 1 minus pi, in this case, we get 83 times 0.67, which gives us 55.6, again greater than 5. So we know we can use the normal approximation as the estimate of this binomial. So continuing on, our z star, our test statistic, comes on out to be p minus pi divided by pi times q, 1 minus pi, divided by the number of data points. And for this example, the numbers come on out to be 0.8916 minus 0.33 divided by 0.33 times 0.67 divided by 0.83, or a z value of 10.88. Now, real briefly, I can jump ahead and say, holy cow, Batman, that clearly isn't a far tail, but let's go ahead and draw a picture of what we actually have. So our statistics, we're going to say, again, is the normal distribution. For this problem, we're given a value of alpha, 0.05. We've got a one-sided test, and so we're just worried about our statistics coming out. Are they in which region? And the area under the curve for this 5% comes on out to a z value that's actually equal to 1.645. And so for our test, which is way out here, our results of 10.88. Clearly that's abnormal, and that really takes us to the conclusion that based on that data, we can go ahead and reject our null hypothesis that the proportion of cadets passing is less than 33%, which I guess is probably a pretty good news. If we wanted to continue this on out with this p-value, the p-value associated with the z greater than 10.88 is roughly equal to 0.0. So we've captured everything under the curve up until that point. So if you've stuck with me to this point, bravo Zulu to you. I want to give you a little bit of a reward for listening on in, and that is a little bit of the homework help. So on 1056, what you're going to do, it's going to be a one-sided test, and what I'm going to encourage you to do is to read this. You'll see in the problem statement literally this line right here, test to see if our data is greater than 40%. We've only got a few numbers here, and that's going to take you into using the binomial tables, and that'll have you using the p-values, which I shared a little bit earlier in the lecture. For 1057, same type of problem, if you will, and the last line of the problem is going to set up your alternate hypothesis. Again, a few number of data points, and that'll have you working with the binomial tables. This hypothesis test is going to be using the formulas that were set up earlier for the p-values. And then finally, one example where you get to use the normal approximation, and that's on 1061, one-sided test there. So with that, thanks for tuning in, and happy calculating proportions.